We've learned now about doing calibration for the ocular ruler at lower powers, and we want to put this knowledge to use here and start to measure our specimens out there and get the length. So if we continue with what we ended with in the last one, what about measuring a specimen with the ocular ruler at 100 times total magnification? So remember our two-step process. First thing is, line up your specimen and measure it with your ocular ruler. So I lined it up with my ocular ruler right there and say, okay, this specimen goes from 20 to 50 right here. It is 30 spaces long for that object right there. And now that I've got this, I want to convert that to metric system units right there. So take my 30 spaces per object, and remember at this magnification, 100 times total power, we've got 1/100th of a millimeter for each space on that ocular ruler right there. Your numbers cancel out in terms of the units on top and bottom, and you end up that this object, if I was measuring it at 100 times total magnification, is 0.3 millimeters in size right there. So we can do this measurement in millimeters, and it's really easy to do the conversions to micrometers. So we just take this right here, 3/10 of a millimeter per object, multiply it by 1,000 micrometers per millimeter right there, and that's going to tell us that the object is 300 micrometers. And then this leads to the question, well, which is the correct answer, 0.3 or 300? Well, they're the same answer, just like you can say 1 foot is 12 inches, 36 inches in a yard, 1,000 millimeters in a meter. These are the same measurement right there, just with different units on the end of that process right there. So pretty easy to do our conversion in terms of that initial one from millimeters to micrometers. You can also do your conversion directly into metric units using your ocular ruler measurement right there. So in this case, instead of using 1/100th of a millimeter per space, we can take this factor right here as 10 micrometers per space. So 30 spaces on your ocular ruler is the length of this thing, is going to be multiplied by our conversion right there, and that's going to give us 300 micrometers per object. So regardless of how you do the conversions, you're still going to come up with the correct number, and it's easy because we're talking about factors of 10, which is easy for us to visualize because we're used to thinking about the decimal system in terms of powers of 10. We can also start doing our calibration of the ocular ruler with our 40x objective. And again, think about what happened when we went from the 4x objective to the 10x objective. Our field of view changed. And when you're looking at your stage micrometer at lower power, we could barely see this stage micrometer against the ocular ruler. Well, now if we look over here under the 40 times objective there, not 400, 400 times total magnification, these lines on this are 100 times larger than they are over there. The ocular ruler is still the same. That does not change. What changes is the magnification of your specimen. So if we crop off and blow up our picture right here to see the magnified image of this, you can see that the lines on the stage micrometer are again able to be lined up with the lines on the ocular ruler. So if we take this place over here and say it looks like this area right here going from 20 to 60 is the same at length as one space on our stage ruler right there. And so if we take these guys out, we know that the one space on the stage is 1/10 of a millimeter. So we don't have to put the multiple ones in there like we've done in the previous ones. And that's going to go from 60 to 20 right there. So 1/10 of a millimeter is 40 spaces when we're looking under 400 times total magnification right there. So work out your math like we've done in the other ones. 1/10 of a millimeter is 40 spaces, and that's going to give us 0.0025 millimeters per space. That number right there is a little bit cumbersome. So why not, instead of using 1/10 of a millimeter, use 100 micrometers. Remember, if you take 0.1 millimeters and multiply it by 1,000, you've converted those units into micrometers. So here, 100 micrometers on this side is the same length as 40 spaces on this side, and that works out to 2.5 micrometers per space on the ocular ruler when you're viewing it at 400 times total magnification. And we can do the exact same thing with our 100x objective over here and go in there and take a look, and notice our field of view has changed again. When we look at this, now we're seeing that those smaller lines that were barely visible at the lowest power with the 4x objective dialed into place, well, now that we've got the 100 times dialed in, those small lines are being magnified a lot more than they were before. And so if you go back and look at the lines that I showed in the beginning in my little cartoon, we've been using these bigger lines over here that are 1/10 of a millimeter or 100 micrometers. And one of those spaces on the stage micrometer is broken up into 10 smaller spaces. So those guys are going to be 10 micrometers in between each of these lines on our stage micrometer. So think about that. Now we know the size of these things that we're using. Now we can look at this and say, hey, this distance between these guys right here, the big lines, it's 0.1 millimeters or 100 micrometers. For the smallest lines that are out there, those guys are 10 micrometers in between each of those lines on your stage micrometer. So we can look at our ocular ruler that is being measured up against our stage one right there. And if you look closely at this, what you can see is it goes from 0 to 100 spaces right there is the same length, apparently, as 10 of those smaller spaces on this stage right there. So 10 times a 1/100th of a millimeter, or 1/10 of a millimeter, is the same as saying 100 spaces on the ocular ruler right there. Work out your math like we've done over and over, and this is going to come out to 0.001 millimeter, which you can write if you don't mind writing a lot of zeros. But for me, I would rather do this conversion right here, because if you look at that, at 1,000 times total magnification, each of those spaces on the ocular ruler is 1 micrometer long. Makes the unit conversion in your measurements really easy to do. And so if we look at these conversion numbers for each of the objectives that is out there, with your 4x objective dialed into place, the distance between each of those lines is 0.025 millimeters or 25 micrometers. When you go up in power, your specimen appears larger, but the ocular ruler doesn't change, which means the distance between those lines has to be smaller. So here it's 10 micrometers or 1/100th of a millimeter. But this is easy to remember. 10 times magnification for the objective, it's 10 micrometers. And if you look at this, if you go up in power 10 times, going from the 10x objective to the 100x objective, notice what happens to the distance between the lines on the ocular ruler. It goes down. So you increase the magnification 10 times, your scale has to go down the same amount that you're magnifying. And it also works when you look at the 4x objective to the 40x objective. It's getting 10 times smaller when we go through this process. So how do we put this into play? There's, again, those 2 steps that we use when we're measuring the length of our specimens that are out there. We take and center our specimen and measure it. And remember, when you're using your ocular ruler and you're going from one power to another, always center your specimen around the 50, because if it's centered over here and you go up in magnification, now it's going to be magnified, and or you're going to be looking at a region where your specimen isn't going to be, because you just magnified over here in the center. So always want to try and center and measure your specimen as you go up in magnification there. The second step is to do that conversion in our metric units so that we can get something in international standard units for reporting. We can take a look at this one with an actual specimen. These are some yeast cells, and here we've got the 10x objective dialed in, so 100 times total magnification, and this one over here where you're looking at it 400 times total magnification. Which of these do you think is going to give you a more accurate measurement? This one, you can see the cells. But remember, when we look at our calibration for these, each of those lines here is a 10 micrometer space. And when we get over here, now we're looking at 2.5 micrometers. So this more magnified version is probably going to give you a more accurate measurement of your cells because you're using a slightly bigger scale right there. What about this? These are two images of a protozoan parasite known as Balantidium coli. This is the specimen magnified 100 times total, and this one 400 times. Which would you feel more comfortable doing the measurement? And if you look at these two, it's a lot easier to measure this because it's a larger appearance to the specimen that's projected against our ocular ruler right there. So we can take this thing and do our two-step process to be able to measure this specimen accurately right there. If you take this and draw a line across it like I did here, and then I just migrated that line up there, you can see that this goes from about 54 spaces to 25 spaces. So that is the length of your cell that you're looking at right there. Well, we know our total magnification, which means we also know our conversion factor. And with your 40x objective dialed in place at 400 times total magnification, it's going to be about 2.5 micrometers per space. This cell that we just determined is about 29 spaces long right there. And so that's going to give us 72.5 micrometers for the width of that cell right there. And we could do the same kind of thing if we're looking at this. This is a cross-section of a mold or a mushroom-like coprinus specimen. And you can see some of these things are really small, and I would not trust the accuracy of that measurement. But when you go up to a higher power, now you could more accurately measure the length across this part of the coprinus specimen. And then sort of the last thing to think about is, what about average sizes that we keep seeing in the lab manual? Well, say you have a string of cells that I've drawn right here, and you've magnified these cells 400 times total with your 40x objective dialed into place. And say your ocular ruler looked kind of like this. I've blown this up in the cartoon so that it's a more readily visible. You center and measure your specimen with your ocular ruler right there. And you go in and look at this and say, okay, this goes from 0 to 20, and I've got 1, 2, 3, 4, 5 cells right there. So you come in and you center and measure your specimen, and then the second thing, we do the conversion. We take that measurement into our metric system units. And with that 40x objective, we've got these two conversion factors that we can use. So effectively, we're converting 20 spaces on the ocular ruler. We can take this number, 20 spaces, and notice instead of saying per object, now I'm saying for 5 cells right there. And then you've got your spaces on top and you've got your spaces on the bottom. Those are going to cancel out, and you're going to end up with 0.05 millimeters for 5 cells, and then you divide that thing out and you're going to end up with 0.01 millimeters per cell, and that's giving you your average size right there. We can do the same thing, and again, I prefer to use this micrometer because it's a little bit easier. You don't have to write as many decimal points and zeros there. 20 spaces for 5 cells multiplied by 2.5 micrometers per space, because we are using our 400x objective, is going to give me 50 micrometers per cell per 5 cells, or 10 micrometers for 1 cell. So there's a lot going on with this, and in lab you're going to be taking some prepared specimen and doing what I've done in these last few parts of this video here. You're going to be measuring single isolated cells at different magnifications, say 4x and 10x, and then determining the size, and the numbers should be relatively close to each other.